Hi, and welcome back to the course on distributed systems and security. We were talking about replicated state machines. So just to remind you, we're trying to construct a system here running a so-called state machine, M, and we want 4 copies of it, for example, running on different servers, such that if one of them will crash, we can still access the system. And then we want this to appear as 1 copy of M towards some clients. And we saw that one way to do that is to make 4 copies and then try to run them on the same sequence of inputs. So the following lecture is then just about how to get a replicated state machine from a so-called totally ordered broadcast, and what is that. And I think this will be the shortest video in covering the book. But let's do it. Okay, so we have said so far that our plan to implement replicated state machines is to have 4 copies of the machine starting in the same state, make sure the system is deterministic, and then run it on the same input. We have seen now several times in the sections on consistent communication and synchronous broadcast and asynchronous broadcast that sending the same inputs to all machines in a system is not easy, but it's something we know how to do already, and we called it broadcast, right? So we could just say that whenever someone wants to give an input to the system, they take the input that they want, and then they broadcast it to all the servers with the level of security they want. For example, security against Byzantine corruptions of up to sharply less than 1/3 of the servers. That's what we would know how to do in an asynchronous system, for example. And then the servers, when they see this input, then they'll just take their current state, run on this input, go to a new state, and produce the output that the state machines produced. So why doesn't that work? I think some of you have already thought about that. And if you want a few seconds more to think, push pause now and then think, what is wrong here? It's not complicated. It's something very simple, so try to look for it. Okay. So what is wrong here is that just because broadcast guarantees that when I send something, then everyone else will be going to see the same message from me, it doesn't guarantee, and we've actually looked at that in consistency, right? That if 2 honest parties broadcast at the same time, that the messages don't come in different orders at different times. So we need to fix that too. So we need a notion of broadcast where when an honest party sends a message, everyone gets the message. And no matter who sends the message and who they collude with up to some corruption level, the same message will always be perceived as having been received from some even consistent server. And they should also be on the order. Right? And it turns out that this last part is harder than it sounds, particularly in asynchronous systems. But let's then say we have that. So let's say we have totally ordered broadcast, then we can do replicated state machines. Again, we formalize what is totally ordered broadcast using an ideal functionality in the book, but in this case, it's rather simple to do just with properties, so let's do that. And in fact, if you have in your head the ideal functionality for replicated state machines, then the one for totally ordered broadcast is the same one, but where the state machine is just a trivial one that for each input copies it to an output. Because then we had this thing that everyone sees prefixes of the same thing. Yeah. What's the properties we want from totally ordered broadcast? Well, first of all servers should broadcast a message. So we imagine a system now that if you're a client and you want to give an input to this replicated system, you give the input to one of the servers that will then broadcast it to all the other servers for you. And then we say that all servers should receive the same messages in the same order. Okay? And again, we can't just say that at any point in time they'll receive the same sequence of messages because some of them might be behind. So what we say is that there is a sequence of messages such that the output of any server is a prefix of the sequence. Okay, so there's a well-defined sequence. Say the sequence output by the server having outputted most values right now, and the output sequence of any honest server is a prefix of that one. I mean, they will eventually catch up, having received the same messages, but at this point, some of the other servers might have received yet new messages, but they go through the same sequence. And in this case here, liveness is also then rather simple to specify. We would just say something like, if an honest server gets an input X, then all honest servers eventually output X. By this, I mean, so if some server is given, an honest server is given X, I'm a client, I would like to give an input, I give it to some honest server, then it should at some point appear in the sequence. That would also be nice to have. That kind of combats these worries I touched briefly on in the previous video with fairness. But that's kind of all we want to say about liveness. It might be that some inputs come much later than other ones. They could be delayed if someone is trying to send some my inputs. But as a minimum, let's say that if an honest client gives to an honest server an input, it will eventually enter into the sequence. That would be nice to have. Okay, so that's what we want. Let's say we can do that. Then obviously we can do replicated state machines, right? So the way we will do it is we take a copy of the state machine. Each server will start it in the initial state. Whenever a server gets an input that should be entered into this running M, it will take it and then send it on the totally ordered broadcast. Not do anything else yet, it sends it. And then all the servers will monitor the totally ordered broadcast, and as inputs come out of it, they take these outputs and they run their local copy of the state machine on it. And then they output this Y here, the output that the state machine produces, and that's it. Okay. And that's because, I mean, trivially, we have said this thing is deterministic. So if it's in the same start state and goes through the same inputs, gets the same inputs, it will end up in the same state and produce the same outputs. And we have said that totally ordered broadcast is something that delivers the outputs in the same order at all clients. So it just trivially works. And they also have this nice fairness thing that if an honest party gives an input to this replicated system, now it will eventually actually contribute to running it. Okay, so that's what there is to that. So we see that once we can do totally ordered broadcast, then it's completely trivial to do replicated state machines. And of course, vice versa, totally ordered broadcast is a special case of replicated state machines, namely the trivial one where the outputs of the system is about just the inputs. So there's no way around it. If we want to, in general, solve the replicated state machine problem, we need to solve the totally ordered broadcast problem because it's a special case. And we have seen that if we solve that special case, then solving the general case is completely trivial, right? So this teaches us that replicated state machines, in the strongest favor, is really just about doing a good totally ordered broadcast. Okay, well, that's kind of maybe not completely trivial when you begin. Like, how would you implement something, like Amazon or Google Docs, anything like this? We have some kind of system where people give inputs and get outputs, and make sure that they eventually see the same thing. Well, it's really just about totally ordered broadcast. There's a lot of optimizations you can do after that, but that's a master level course here. But at the core of that problem is really just this thing, make sure everyone eventually sees the same sequence of inputs. For example, in Google Docs, make sure that everyone eventually see the same sequence of edit commands, inject. So let's focus on that and become very good at that. And then we also know how to solve the replicated state machine problem. Okay, so we will do that. We will look at doing totally ordered broadcast in 3 flavors. We'll do it in the synchronous model, we'll do it in the asynchronous model, and we'll also do it in the partially synchronous model, or rather actually the semi-synchronous model. We'll also do it in the eventually synchronous model. Okay, they are of course very closely related, but we actually do it in the eventual synchronous one in the book. And then that's it on how to implement replicated state machines from totally ordered broadcast. And we'll then in the next lectures really just dive into the nerdy stuff of then how do we make sure that everyone sees the same messages in the same order. So we're now talking about how to implement totally ordered broadcast. And we start with a rather simple setting, namely the synchronous one. Let's say we have full synchrony in the system. Let's allow ourselves to use the round-based synchronous model where communication proceeds in rounds and we are synchronized on the clocks, at least within the length of a round. How would we solve this? To remember that the hard problem is to make sure that everyone sees the same messages in the same order, even if there's some kind of attack on the system. It's rather simple in the synchronous model. I mean, we have some powerful protocols there, in particular the Stolif Strong protocol, which allows us to do broadcast. So it allows someone to send the same message to all other parties in the system, even if up to all other except one or two of the servers are corrupted. So we could imagine that what we're doing is that when an input arrives to the system, I mean, it's given to one of the honest servers that will just flood it to the other ones, say using one of these unstructured peer-to-peer networks, just push it out to everybody. And then in each round, all the servers will just take the set of messages, outstanding messages. That means the messages they saw on the network, but still were not defined to be in the total order. Put it into a block. I mean, put all the messages into a message that we often call a block, and then just broadcast it to everyone else. So they just all do that. And the reason why we broadcast the block is to make sure that we agree on what everyone is reporting. And then we could just say, you know, now we get a block from all other servers, and they are guaranteed to be the same. So we could just take the union of them, and then in some well-defined order, let's say lexicographically, take all the messages in the union of the blocks and then output them one by one on our interface. Then because we're seeing all the same blocks and we order them in a deterministic way, we're now delivering outputs from the system in the same order. And by collecting a block from each of the other servers, we have a very fast throughput here in that if a message is given to a server, it will appear in the next kind of round of output. Of course, in practice, there'll be some bound on how big these blocks can be and so on. And that works, and that would be one way to do it. It turns out this is definitely not how you want to do it, because as we already saw, broadcast is expensive, right? We saw it, I mean, you're sending something like n squared or n to the cube messages in the Stolif Strong. So if you have 100 servers, then that would be about 1 million messages per broadcast. So if one broadcast is expensive, certainly n broadcasts are more expensive. So we don't want all servers to broadcast their message in every round. And it turns out we don't have to. We can just let it go in round robin and then say in each round, one of the servers will broadcast the next block. There are two versions of this being used in practice. One is where you have a sequencer, which is just one server that's doing this job, broadcasting the next block in every round. The problem with that is that the sequencer, if corrupted, could do secret censoring, ignoring all messages coming from me. So if you want a little bit more security, you let this role go round robin. So I mean, in each other round, it's another server doing this job. And thereby we get fairness. And that's the version I want to show you in a little bit more detail. So this is the full protocol. It's not as bad as it looks. It has two logical systems. One is the flooding network, where if a client wants to give an input, it will be put on the flooding network. I mean, we could either imagine it's given to an honest server or just directly put onto a flooding network. And by flooding network, I just mean something where if an honest party sends a message on the network, then it will eventually appear at all honest servers. But it could be that if a corrupt one sends a message, it doesn't get I mean, it's not a broadcast thing, it's just for flooding, so that honest parties can be guaranteed that their message will eventually be seen by all other honest parties. And if you're doing some of the exercises in the book, you might have started programming such a thing already, like one of these peer-to-peer flooding networks. Okay, so let's just say we have it, we call it flood. Party I has an interface flood I, and if it puts a message there, it will eventually appear at all honest parties in the network. Okay, then the first logical part of the protocol is just to get incoming messages into the set here of unqueued messages that everyone is holding. Those are the messages that they know should become part of the global order, but that have not been ordered yet. Okay. So an equally good name would have been unordered. Well, now we picked unqueued here. Okay. So what this thing is just doing is, if a party gets an input for the totally ordered broadcast, they start by flooding it. And then whenever they see a message coming out of the flooding network, they take that thing and adds it to the set of unqueued things. So what is this part of the protocol doing? Is just ensuring that if an honest party wants to send a message, it will, within the delivery time of this flooding network, within some reasonable time probably, end up sitting in all these unqueued sets or the honest servers. Okay? So what we want to do next now is to move messages from the unqueued one into the queued one. Here, everyone has a list of queued messages, and we want to do that in such a way that this one is the same at all honest parties at all times. And then that will just be the messages that we're outputting from the totally ordered broadcast. This is done as follows. So initially, let unqueued and queued both be empty sets. Let the epoch be 1. There's something called an epoch that just goes by 1 in each epoch. An epoch is the time it takes to broadcast one message, to broadcast one round of messages. Then we're using a system here called cast also. That's a broadcast system. And it's one where we assume for simplicity that all honest parties will terminate in the same round. So it's a system where we can say, now it's party 3's turn to broadcast. All parties input party 3. And party 3, in addition, inputs a message. They do that in the same round. And then in some later same round, they will not output the message that was broadcast. So this is just synchronous broadcast, right? And if you think back to Dolev Strong, it had this property that all parties ended in the same round. I think it was in round n+2 after starting, or n+1, depending on how you count the rounds. Okay, so let's just say we have that subsystem also. Then the protocol goes as follows. So this epoch here will be increasing, and we say that the leader in a given epoch, that's the party pi, where I equals the epoch number, and then modulo n is the number of parties in the system. Okay, so in epoch 1 is party 1 that's broadcasting, in epoch 2 it's party 2, and so on up to party n, and then in epoch n+1 it's party 1 again that's doing the broadcasting. Okay, and that's just the party or server that we call the leader. Okay, so what we do is the following: the leader will create a block, an unordered block here. It's just all the outstanding messages it has. It's all the unqueued messages, and then it removes the one that was already queued by itself and other leaders in the past, and it will send out all the outstanding ones. Now, in practice, of course, this one could grow so big that you can't reasonably send it out in one block. Then you might have a max size and so on. But for now, let's just say we have infinite bandwidth, and do. Then this is what you do. Take all the outstanding message at this point where you're the leader, or the unqueued one, then remove the queued one. Those are the outstanding ones, and then broadcast it. So PI will input on the cast system this block here, and everyone else will input PI to the cast system, indicating that it's PI's turn to broadcast. And then they wait. And this, if it's Dolev Strong and there's 100 servers and you want to tolerate the 99 of them are corrupted, this will now take 100 rounds, because that's how long Dolev Strong takes, right? So it's running, but in some later round, they all get an output. So all PJ here, when this block here is being outputted, it's being received on this port here from the broadcast system. Then they will add U to Qt and output the new elements on the totally ordered broadcast port here in the order in which they appear in this list here. So U here was sent as a list. So they all outputted in the same order. And then they just go up here again. Then it's the next leader's turn to create a block, broadcast it, and we output in that order. And that's all it is. Right? So here epoch is incremented and we go to step 2 again. So that's really all there is to it. So it means we just go through a round of synchronous broadcasts. Right? And then one can, I mean, it's rather obvious that this works, right? But I mean, we can take a look at the properties. So first, safety for totally ordered broadcasting. That was this thing that all parties at all points in time have output a prefix of the same sequence. This is obviously the case. If we're at a point where all servers outputted the last block, they really outputted the same thing. But then again, there might be a slight difference in physical time between when they output the block, but certainly they will eventually all catch up and have outputted the same sequence. We also have a nice liveness property in this system here, namely that if an honest party inputs an X to the system, then because we're flooding it, it will very soon be sitting at all honest servers. And that means it will enter the output sequence at the first point in time when honest server is leader, because they will take all the outstanding ones and put them into the block. So there's no censoring in this system here.